Let's talk a little bit now about permutations. Here I have a formula for computing the number of permutations, P for permutation. N stands for the number of objects I have to choose from, and R stands for the number of those objects that I'm going to select. Then I have this formula where I take n factorial, we talked about what the factorial meant a while ago, divided by n minus r factorial. So you just do that subtraction, and then you take the factorial of that as well. But before we get into actually using that formula, let's take a look maybe at how, or what a permutation actually even means. Like if I have, for instance, let's say I had the word cat for a second. If I wanted to see how many unique permutations I could come up with using two letters in the word cat, I could start off with C. I could follow that with A. I could start off with C, and I could follow that with T. Another option would be I could start with letter A, and I could follow that with C. I could start with the letter A and follow that with T. And then finally I could have the letter T, and I could follow that with C, or I could follow that with A. Those would be my options. So if I wanted to know, using those three letters, how many unique permutations or arrangements I could make of two letters, in this small example, I've listed them all out, and I can see that there are, in fact, 6 of those. Combinations are a little bit different. Combinations, the order doesn't the order doesn't matter. It doesn't count as a different thing. Like CA and AC would count as the same thing in a combination problem, but they are different in a permutation problem because permutations, the order is specific. I always liken it to a password. It definitely matters what order I type my letters in for my password with that. Several students often say they have combination locks on their lockers. I disagree. They actually have permutation locks on their lockers because the order that you put those numbers in is specific and it doesn't matter. If there's truly a combination lock, you should just be able to throw the 3, 4, however many numbers there were in any order and it should work, and that's not the case at all. I'll go ahead and use this example to actually compute this. Let's say I want to see how many. I was trying to figure out how many unique two-letter permutations there were using only the letters in the word cat. So I had 3 letters to choose from, and I was choosing 2 of them. So let's go ahead and look at that. Let's say I wanted to compute 3P2. Let's go ahead and plug that in. And I know what the answer should be already. I should get 6. I just did it a second ago. So n factorial, n being 3. So on the top I have 3 factorial. On the bottom I have 3 minus 2 factorial. So on the top, that's 3 factorial. On the bottom, that's 3 minus 2, which is 1 factorial. 3 factorial means 3 times 2 times 1. 1 factorial would just mean 1. Those would cancel, and 3 times 2 would be, in fact, 6. So I know that wasn't a very exciting example. With that, let's go ahead and try to compute something else real quick just to see how this works with permutations. Let's say I wanted to do 10P4, like that. So I had 10 objects, and I wanted to choose 4 of them from that where the order is important. The order is specific. Maybe it's like I'm making a playlist of 4 songs from a group of 10. So whichever one plays first is important to me versus second, third, fourth, and so on for that. So let's plug these into the formula. I have 10 factorial over, on the bottom, I have 10 minus 4 factorial. So that's 10 factorial over 6 factorial. Now I'm going to show you a little bit of a trick here for simplifying this because these numbers can quickly get huge and out of hand and potentially even overload the calculator depending on how large these numbers end up being. But what I'm going to do is I'm going to start breaking down the 10 factorial until I hit this factorial on the bottom. So 10 factorial means 10 times 9 times 8 times 7 times, and instead of saying 6 times 5 times 4 times 3 times 2 times 1 the rest of the way down, I'm just going to abbreviate that with this 6 factorial. That's what it means. It means times 6 times 5 times 4 times 3 times 2 times 1. Hopefully you can see by doing that, I also have 6 factorial in the denominator, so those 2 things there could just cancel out, and I would be left just needing to compute 10 times 9 times 8 times 7 to have this problem worked out. So I'll do that now. 10 times 9 is 90 times 8 times 7 is 5,040. So if I had 10 objects and that were all different, and I wanted to pick 4 of them and arrange them in a certain order, there would be 5,040 different, unique arrangements I could make of 4 objects out of that group of 10, with this one being first, second, third, or so on. Like that. I think that's pretty cool.